Hi, everybody. It's a friendly audience. That's reassuring. Um, Thanks for being here. Hope you're comfortable. So we've been asked by the conference organizers to remind everybody to network just as hard as you can. So when you get a chance, introduce yourselves to your neighbors. Meanwhile, we're going to get started. So welcome to our talk. The title is Evolutionary UI, Change as a First-Class Citizen in the Modern Frontend World, which is a long title, but hopefully it will be elucidated as we go along. So before we dig into the meat of our talk, we would just like to set the context a little bit about who we are and how we got here. Also, if you can't hear me at the back, please let me know and I'll be a bit closer to the mic. So, hi, I'm Rufus.
And I'm Giamir.
We are both senior developers at ThoughtWorks. We co-founded and now co-organize the ThoughtWorks frontend community, which is an internal community of practice at ThoughtWorks that focuses on promoting and encouraging front-end engineering excellence. And we're here today because our colleagues wrote a book, which you may have seen around. It's called Building Evolutionary Architectures, Support Constant Change. And we were inspired by this book because it provides some insights into how to build elegantly extensible architectures that are resilient to change in a good way. Unfortunately, as is often the case with the sort of literature around software architecture, there's no mention made of how to apply this wisdom to UI. And so that's why we're here today. And in fact, I believe that 2 out of the 3 authors are also speaking at this conference, so that's not terrifying at all.
So, this is the agenda for our talks today. First, we are going to give you a brief recap of what is an evolutionary architecture. Then we're going to talk about why investing in UI design is especially important if you want to have UI that scales. We are then going to deep dive into 2 concrete examples of UI architecture built with evolvability in mind. And finally, we're going to wrap up our session by sharing with you all a couple of gotchas we may encounter when we build an evolutionary UI.
So let's get started. First of all, what is evolutionary architecture? This is an interesting audience for us because unlike when we've given this talk previously, I suspect that many of you are familiar with the term. If you've heard of evolutionary architecture, would you raise your hand, please? Wow. That's a lot of you. That's definitely the majority. So for those of you who are already familiar, bear with us. We are going to give a quick high-level overview of what the concepts are so that we can have that as a common basis as we move forward. So let's quickly return to our high school biology and recall that evolution is defined as the cumulative change of characteristics of a population over time, or in software terms, the cumulative change of the characteristics of a software system over time. As we're all well aware, change in software is inevitable. Context and requirements change and technology becomes obsolete over time, so there simply is no way for your system to not change. So an intelligent question that we might ask is, how can we as software architects control and guide this change such that it progresses in a way that is conducive to happiness? Well, that's exactly what the purpose of evolutionary architecture is. An evolutionary architecture is one that supports incremental guided change as a first principle. How does that work? Well, it turns out that humans have been intuiting how to use evolutionary architecture principles for a long time. So there's this concept of a fitness function. And in dog breeding, we've been using it for thousands of years to select for characteristics that we care about, like size, appearance, hunting skills, and so on. We call this artificial selection. In software, we refer to these as architectural fitness functions. They provide an objective assessment of some characteristics that we care about. I'm sure you can think of many that you're already using. I'm going to give a couple of quick examples of fitness functions that are relevant to the UI world. Code quality. So, of course, you might use a code analysis tool to measure cyclomatic complexity and have some sort of gate that enforces a specific maximum complexity for a method. In testing, you might have a minimum threshold that ensures that at least a certain number of lines and branches are covered. Accessibility, you might be using a tool like Pally or Lighthouse to ensure a specific compliance level of the web content accessibility guidelines. And performance, so you might use what we call a performance budget to keep yourself honest to a bundle size that you don't want to overextend. So something to note is that these fitness functions can be automated, but they can also be manual. Of course, as engineers, we love to automate things and then forget about them. However, fitness functions can still be valuable even if they're simply written down and revisited regularly. And we'll see some examples of manual fitness functions as we move forward in this talk.
So we now seen like a couple of UI fitness function, and then let's now try to explain why it's worth to set up some of these fitness function when we build our UIs. So of course, in software development there are no free meal, and maintaining fitness function is effortful. So we may logically ask ourselves, do we need to account for evolvability in our UIs? So how many of you in the audience are already familiar with the concept, with the design payoff line? No one. All right. So I'm gonna give you a brief overview of what is this, what's this line is about, and I'm gonna help myself with a graph that I kindly borrow from Martin Fowler's website. Probably there are more people in the audience that know Martin Fowler. How many of you know Martin Fowler? It's our chief scientist at, oh, everybody. So, okay. So it's nothing new. It's something that he came up with. So in this graph, we have, in the vertical axis, we have cumulative feature that we are adding to our UI system. While in the horizontal axis, we have time. So when we want to build a UI system, or any system really, we essentially have two approaches. The first one is to actually start developing without really having an architectural vision. This will give you a boost, of course, at the beginning, but eventually you will reach a stage where you accumulated so much of this so-called tech debt that making a change in your UI is going to be really, really hard. The other approach that you have is to actually invest in more time at the beginning on setting solid bedrocks for your system. And of course, with this approach, at the beginning, you're not going as fast as the former one, but you will eventually reach a stage where the investment that you made will pay you off. So you can now draw the design payoff line. So below this line, it's okay sometimes to trade off good design for time to market. So this is the classic scenario when you have to build a prototype or a proof of concept. But above the line, there is not really useful trade-off. So you might now think, okay, the amount of complexity that lives in our UI will never reach a stage where it's actually worth to investing in good UI architecture. But the truth is that scaling UI development is harder than you think. And here is why. So the UI space is evolving, it's moving very fast, especially on the web. So every day, there is some new frameworks coming out, some new library coming out. So I like to think of JavaScript this happy puppy, running fast, discovering new tools, new best practices every day. And although I love to be part of the JavaScript community, I have to admit that keeping up with this pace can be challenging, especially for big enterprise. Nice picture, huh? Another challenge that we have in the UI is about keeping UX consistent when we have multiple teams, sometimes even distributed, working on the same application. So one classic manifestation of this challenge is when you basically start observing different parts of your application behaving differently depending on modules that are developed by different teams. So when we do development at scale, UI development at scale, keeping UX consistent, it's a challenge. So, and as our front-end practices best practices are solidifying, like we also need to allow for our UI testing strategy to evolve. So it can be harmful to make the assumption that traditional testing strategy will work effectively also for UI. And the final challenge that I want to talk to you about today is about partitioning complexity. And this one is one that applies to all the areas of software development, of course. But in UI, we have some very specific, unique challenges, because we are often developing for client devices with unpredictable capability. So how much CPU resources or how much network bandwidth my application can account for? Will I be able to provide offline capabilities to my user? So partitioning complexity is a topic that is getting more and more traction, in the software industry. And this morning, I was going through the schedule of this conference, and I actually observed that there are at least 3 talks, at this very conference, that they're actually addressing this challenge. So it's true, maintaining fitness function is effortful, but it pays off, especially if you want your UI to scale.
All right, so now that we've covered a brief overview of what evolutionary architecture is, and we've hopefully convinced you that it's worth thinking about in the context of your UI, let's get into the weeds and see how we might apply some of the evolutionary architecture principles to your UI development practices. So let's talk about testing. As Giamir has mentioned, testing can be challenging, particularly when we're using modern front-end development practices and trying to combine them with more traditional or old-fashioned testing practices. So how do we know if we're struggling with this? Well, let's consider a problem statement. We are architects, and our teams are spending a lot of time refactoring their UI tests. This might seem like a trivial issue at first. It might not feel as though it will result in a big delivery risk. But actually, if every time a new feature goes in or a bug is fixed, we're spending time refactoring the tests, and sometimes it can take a very long time to do those touch-ups, this really scales poorly. So at scale, once you have multiple teams, you can be looking at really quite a lot of time that goes into this that could otherwise be spent developing your product. So to understand why this happens, we'll have to take a quick detour and understand what modern UI, component-based UI development looks like. So let's consider the case where we have a team that's developing a shopping cart component for your unnamed e-commerce website. This shopping cart component probably breaks down into smaller components, let's say a cart icon, a nav that lets you navigate through several pages of all of the stuff that you shopped for, and then, of course, several items. Each of these child components requires data that it requires to turn and render some view. And now you might ask, okay, it seems like they're really dependent on a lot of data from the outside. Shouldn't a component be independent? And yes, ideally so. But if you look at the data that's required, you'll see that actually a lot of them depend on shared contexts. So if you were to have them each load and manage their state independently, not only would you be dealing with redundancy and unnecessary constraint on the limited resources that you have on the client, but you're now also having to solve the problem of keeping the states in these different components in sync. And so the usual solution to this problem is to externalize state that's shared, either into some sort of wrapper component like the shopping cart itself, or into maybe a more official state management solution such as Redux. And so because you're separating your state logic and your view logic in this way, you quickly end up with components that take quite a lot of data from the outside. This is a real problem. So while the shopping cart example is contrived, this is a real component that I am complicit in writing. It did not start out like this. My team created this component about a year ago. It was lovely at the time, and now it looks like this. As more use cases were discovered and the component had to be kept generic, really, you can see that there's been an explosive growth in the props or the surface area that this component depends on. So how do you test something like that? Well, let's review our traditional received wisdom about testing. So I'm sure we're all familiar here with the testing pyramid. So the test pyramid outlines 3 strata of testing. You have unit tests, integration tests, and end-to-end tests. Unit tests are supposed to be the cheapest to run, write, and maintain. Integration tests less cheap, and end-to-end tests the most expensive of all, which is why you have the most unit tests, followed by less integration tests, and the fewest end-to-end tests, thus the shape of the pyramid. To understand why the test pyramid makes sense, you have to understand that there's really a couple of central assumptions that are being made. I'm going to break these down into 3 assumptions. One, that units have small surface area. For example, in the case of a Java class, you have a single public method, maybe some private methods, such that your tests can depend only on a single piece of exposed API, and the class can be freely refactored internally whilst keeping the external API stable. 2, that you can get good confidence from having many unit tests and few integration tests, accounting for the shape of the pyramid. And 3, that unit tests are significantly cheaper to write and maintain than integration tests. So let's come back to our shopping cart example and see how those assumptions actually hold up. So in the case of unit testing, we would likely be looking at testing each of these constituent components in isolation. So assumption 1 was that units have a small surface area. But actually, as we've seen, UI components often have a large surface area, props, which can quickly couple the tests you've written to the implementation, such that every time that the surface area changes or something changes in how you're managing your state, now all of your tests break. Assumption number 2 was that you can get good confidence from having many unit tests and few integration tests. Not really true. Since you're almost certainly separating your state management from your view logic, and you can certainly test each of those things beautifully as units in isolation, it is still nevertheless very easy to get into a situation where all of your unit tests are passing and yet your application is broken in production. Since the behavior that the business actually depends upon is an emergent property that only really occurs when you combine the state and the view rendering logic together. Assumption 3 was that unit tests are significantly cheaper to write and maintain than integration tests. Again, not really true anymore. The tooling that's available for front-end engineers today is really quite incredible. So tools such as Jest, Enzyme, React Testing Library make it really quite easy to deeply mount entire cohesive pieces of view and interact with them like a user would. So we're really talking about an additional expense that's in the magnitude of milliseconds to seconds. So here you really have to think about the trade-off that you're making. So let's come back to our problem statements. We're spending too much time refactoring our tests. So our stated goal is loose coupling of tests to implementation. So that's our overall architectural characteristic that we're trying to protect. Let's write some concrete fitness functions to protect that characteristic. 1, no shallow rendering. For those of you who are not familiar, shallow rendering is a way of test rendering your components that isolates them, so you're basically getting only a single slice of the component hierarchy in your tests. Many people have argued that this encourages testing practices that are undesirable because they do make you depend on the implementation of the component a lot of the time. If you wanted to automate this, Giamir has kindly written an ESLint plugin for you. You can pop into your CI. Here's a manual fitness function we could try. We could record this into our ADR and frequently do an audit as a team. We could decide as a team that we will no longer allow assertions on props. We've seen how fickle and explosively prone to change the prop API of a component can be. This is a more controversial one, but we could, as a team, try to restrict mocking to only the network level. This, again, would prevent you from having to look at the implementation of your components under the hood. So your test could be almost entirely agnostic of how the components work. So coming back to our shopping cart example, Let's see how these fitness functions fare in this case. So if we're trying to unit test each of these components independently, immediately no shallow rendering fitness function fails because it's not really possible to isolate any of these units unless you're doing shallow rendering. If you are trying to assert each of the, if you are trying to test each of these components in isolation, very likely your second fitness function fails too, because each of these components probably does almost nothing. All of the state management is somewhere else, and so quite likely the only thing it does is either render some view, call some functions, or pass props on to somewhere else. So it's very likely that your assertions are, at least to some degree, aware of the implementation of your components. So that one fails too. And then 3, only network mocks. This one definitely fails because those components here have no idea where your network even is. So all their state is being loaded somewhere else, and these components are simply receiving it. So if you wanted to redo your testing strategy to make these fitness functions pass, you could move your tests up a level. So we could say, let's start testing our component at the shopping cart level. So then we don't need shallow rendering anymore, so that function passes. We don't need to, or actually we cannot assert on our props anymore because we don't see those props. They're completely obscured from our view. And actually, using network mocks might be really advantageous because it means that we can now use the entire shopping cart component, view logic, and state management logic combined, and simply point it to whatever expected API you have. So now we've arrived at what we like to call quantum level UI testing. People have different names for it. Some people call it subcutaneous testing, which is confusing because that's already a thing. Some people like to call it user journey testing, which is confusing because that's already a thing. Some people like to call it domain testing. We like quantum level UI testing because in evolutionary architecture, an architectural quantum is a component that has high functional cohesion and is independently operational / deployable. In the example of the shopping cart, only really once you reach the shopping cart level do you have something that is functionally cohesive, valuable, and deployable in and of itself. Of course, it's not a panacea. It does meet our need, our stated goal of loosely coupled tests, but if you care about TDD, that's a lot harder. So this is something that at ThoughtWorks we would struggle with. I've had many of these conversations. Of course, a test that is unaware of the implementation, almost by definition, cannot drive an implementation. So a lot of the times, the kinds of tests that you write are almost more like BDD, like business style requirements. User does something, thing happens. So here you really see the power of evolutionary architecture to enable you to make trade-offs at a high level.
All right. So we've already seen that partitioning complexity, like in the UI, is especially hard. So let's say that we have this problem. Like we are not able to provide value to our final user as fast as if we would like because we have cross-team release dependencies. So like teams are actually like depending on each other in order like to ship a feature to production. So let's imagine that we are in this scenario. We have a lovely newspaper website here, like it's a very simple one, has a search bar on top, a content section, some ads, and a related article section as well. And because, you know, it's 2019, probably our organization already went through the efforts of actually organizing their team around a product or a specific capability like of the business. So we will have a team that is responsible like for the search capability, one for the content, etc., etc. And you know, like because it's 2018 again, like we're also doing these teams are doing microservices. But then you have a front-end monolith on top of all these microservices that actually consume information from all these microservices. And you also have a user experience team that is gatekeeping this horizontal layer. So, of course, like when, for example, the search teams need to deploy a feature like to production, like they need to open a pull request like to the user experience team, like so that their UI can actually go through and see it in production. So you can see that at least two different applications here that needs to be redeployed, and there is this dependency on each other on the teams. And this is not even the worst case scenario because it can happen that these teams are not even allowed like to open pull requests, but work needs to be prioritized in the backlog of the user experience team that is responsible for the front-end monolith. So we want to fix this problem, of course. And the first things that we are going to do is to set a couple of evolvability goals that we believe that will help us to solve the situation at hand. The first evolvability goal that we want is for team to be able to deploy independently the UI. So we could set up, for example, a manual fitness function like this one. Let's say that in order to ship a change to production for a given product, only one application needs to be redeployed. So, for example, like going back to our example, like if the ads team needs to change something in the UI, like they can only deploy their own service, and they are not allowed like to open pull requests or told to the other team. Another evolvability goal that you may want to set is about scalable development. So let's say that our newspaper website is pretty successful, and the business wants us to introduce a new capability, let's say a short list. So we want to make sure that when we introduce this capability, we don't slow down the delivery of the other team. Of course, this capability will have a UI as well. In here, we could set up a fitness function, for example, that is a little bit, for example, for the time, for the code changes, to get to production. This is also sometimes known as cycle time. And you could, for example, set a hard limit of 30 minutes, from when you push to master, till you see your changes, to production. And you can even think of automatizing, this fitness function in your pipeline. Cool. So now, going back to our example, we have this front-end monolith. We already can clearly see that the first fitness function is broken, because in order to ship a change to production, at least 2 applications need to be redeployed, 2 teams need to coordinate. So that's not working. The second fitness function, well, I guess that until we have just this capability, maybe it's fulfilled, but then as soon as probably we add more capability, what happens is that we are adding also extra work on the user experience team backlog, right? And of course, feature will take more time to get to production. So we want to fix this. And one way to go about it is to actually split our front-end monolith and identify UI, part of the UI that are related to one of the business capabilities that we have, take this part of the UI and give the ownership of this to the respective teams. Then we also want to, basically create a composition layer, as you can see there, that allow for all these front-end to be built at runtime. So guess what? You just reverse engineer microfrontends. So how many of you in the audience already heard about microfrontends? That's a lot of you. How many actually are using them in production today? Oh, that's quite a few people. Okay. So I didn't want to come up with my own definition of microfrontends. There are a lot of definitions out there in the wild. So I decided to borrow one from Cam Jackson, an Australian colleague of ours. So microfrontends are an architectural style where independently deliverable front-end applications are composed into a greater whole. So, of course, as always, there's no architecture that is good in itself. And microfrontends are not an exception. So we pick microfrontends because we want independent deployments and scalable development. But if your first priority is about enforcing UX consistency, we would probably think twice before introducing microfrontend, because of course, like, it's easier, like on a front-end monolith managed by one single team, to enforce UX consistency. Microfrontends have also been received like, in the community like on a controversial way. And that's why, like, as you can see here at the bottom, like, they have the capability of potential for heterogeneous system, which means that, you know, you could have like team A developing like their front end with technology, like with a technology like React, and team B using Angular or Vue.js. So, of course, this is a pros when, for example, you have a legacy technology on your UI and you want to slowly like move away from this legacy technology. They kind of allow you to use the same strangler pattern that we are all familiar with probably in the microservices. But you also need to make sure that people don't start to abuse like this power, because of course, like all of this team using different technology they will result like on a increase on the byte size that we send to the final user, and therefore like they will deteriorate like the final user experience. So you could, for example, like set a fitness function, like Rufus was mentioned before, that check your bundle size to make sure that you're not shipping to your user too much kilobytes. So I'm now gonna stop speak about microfrontends, but if you are interested in the topic, you should definitely like have a read at this article, like in Martin Fowler website from Cam Jackson. It goes in detail like about this technique, and I think it's the next session. Yeah, in the next session, our Thothor Germany head of technology have a whole talk about pattern for microfrontend. So I would strongly recommend to join him.
Just a little bit of light branding there. Great. So we've seen how we can state a problem that we're having in terms of fitness functions, and then allow those fitness functions to drive us towards new architectures that fulfill our wishes. Notably, the architectures that we end up with are not good in and of themselves, but they're good for us because they meet our acceptance criteria, our fitness functions. So let's now see how fitness functions can go awry and how we can troubleshoot them. I love this picture. I just want to know how this situation happened. Maybe it's photoshopped. So what happens when fitness functions collide? Sometimes get asked this question. It's a fair question. It happens. You know, sometimes the things you want are mutually exclusive. Sometimes they're in tension. So Giamir already mentioned the example of wanting scalable development, which often requires a high degree of team autonomy, while it's at the same time wanting to keep UX consistent, or wanting to restrict yourself to a minimum bundle size. Those things can be in tension, or sometimes in open conflict. So what do we do here? RMRF the entire project, throw up our hands and start over? No. As with most things in architecture, these should be catalysts for productive and valuable conversations. So this should be viewed as an opportunity for technical leadership and business leadership to get together and decide priorities. So it's all about trade-offs, as everything in software architecture.
If there is one thing that I learned from being an agile consultant, is that we cannot really predict architecture in advance, because in our job, requirements are constantly changing. Right? So the best things that we can do is actually like bet on some architectural characteristic that we believe at that time like they will help us like to fix the problem at hand. So like for example, like it can easily happen, right, that you start up a new project like with a new team that is not very mature, like on front-end development, and you introduce a code coverage tool, and just to make sure that the team is incentivized like to do UI testing. But with time, it's like, especially if you set a threshold that is very high, you will start to see like tests that are in place just for the sake of making the code coverage tool happy. And this is actually coupling, like, coupling your testing like to your implementation detail. And as we've seen, like from the part that Rufus just explained to us, like it's a situation where you don't want to be because it makes your architecture hard to evolve. So what do we do if we pick a bad fitness function? Like, so we just revisit it. Like, we don't have to be afraid like to revisit. We need to ask ourselves, like, what was the reason why like we introduced this fitness function in the first place? Maybe like now the team is very good at doing UI testing. So maybe you can just focus on trend and don't have a hard limit. So in short, don't be afraid of changing your fitness function because they need to evolve as your UI architecture evolves.
Okay, so if you have understandably snoozed off, this is now your opportunity to get the too long didn't read and come away with some crispy takeaways. So let's dive in. First off, an evolutionary architecture supports incremental guided change over time.
So UI development at scale is challenging, and we've seen like the things like the fast-paced ecosystem, like and testing, partitioning complexity in UI can get in the way like, of shipping like UI that support constant change. So good UI architecture pays off.
To build an evolvable UI, start out by defining what's important for your system. Build some objective fitness functions around them, whether automated or manual, and then apply and review them regularly. And just before we say goodbye for today, here is your regular reminder to please rate and leave us some feedback for the session. We've never done it in front of a crowd such as you, so we'd love to hear your feedback on the session. We'll also be hanging out on the side if anybody would like to chat. We really appreciate your input. And thank you so much. Thanks for coming out.
Thank you.